So all that knowledge is useless, right? It's completely useless. You don't need it for anything.
Our explanation of the convention that we were using was just wrong.
It's possible that some of that is just stupid.
By popular request, I am joined today by Casey Muratori, famed game developer, and honestly, I'll butcher the introduction. Do you want to just take a second and tell us a little bit about who you are, Casey?
Sure. I'm definitely not a famed game developer. That might be a misnomer. I worked on game technology for a long time, actually, at Rad Game Tools, and our tech was used in a tremendous number of games, certainly, but you don't really get any fame for that in the game industry, right? If you're going to be a famed game developer, you're probably somebody who was more on the design side, I would say, right? Look, when you think about household names in game development, it's pretty hard to come by a programmer. Like maybe like John Carmack would be an example, but there aren't very many. Whereas like everyone knows Sid Meier, right? Because his name's on the box. So I worked in the game industry for a pretty long time, mostly on the library side of things. And I've tried some indie game projects myself, but I'm horrible at game design to that point. So that's kind of a struggle for me. I can relate when people tell me about programming and they say they're having a hard time with things. I can relate because I have that problem with anything design related. So I'm like, I know what you're going through. But yeah, mostly I just do tech stuff. And nowadays I do kind of like learning materials, since that seems to be something that people have wanted for game engine stuff. And so, that's been what I've been working on lately. But yeah, that's more or less it. And I think, to the extent that anyone actually knows who I am, it's usually because there was a fairly small number of people who've been kind of out there trying to suggest that maybe like a lot of modern programming practices are going in the wrong direction. They tend to be older people like myself who, came out of a previous era or disciplines. And so, that's more where people have heard of me from, right? It's like that kind of a thing. And not like, I don't think anyone knows about my, the character animation stuff or the video compression stuff I worked on at Rad. I don't think anyone knows, like that would have been by far the most widely used code I've ever done. I don't think anyone cares about that or even knows about that in the mainstream anyway. So.
Okay. So yeah, we're going to talk about computer enhance. I'm assuming that's the educational stuff you're talking about. Definitely want to get to that. I want to just pull a little bit on the thread really quickly about this idea of like game developer versus game designer. You said I don't know if people would know me as a game developer. You're definitely more on the technical side, right? The programming side of game development, rather than, I guess you'd use the word like game designer. What are these job titles like in the industry? Like, how do people think about how their role fits into the production of a game?
Well, there's probably two different definitions you could use. One definition is like is what does the industry mean when someone posts a job description like game designer, right? And then another one is, in reality, if you asked the best game designers in the world and you ask them what is the skill set that they have that is valuable, that like I don't have, for example, that makes them great, right? And those are really two different things. As you might expect, industrialization of things tends to be more about a commoditized approach to that. So when you talk about game design, you're not really talking in an industrial setting about what Jonathan Blow is doing, right? He's doing something that's closer to like an artistic, like forward-pushing pursuit. He's not like, oh, my main job is like looking at spreadsheets of like damage tables that like how much this item is going to do in an RPG, right?
Yeah.
And so I think it's important to separate those two things, because if you're looking at what a typical, I just have a job as a game designer at a company is, that could be very different than what game design is in the sense of I'm going to design a new and interesting game, right?
Right.
You could also draw a comparison like what Richard Garfield does when he designs Magic the Gathering, right, is perhaps quite a bit different than what somebody coming along making a clone-like card game in the wake of Magic the Gathering is doing, right? There's the pioneer higher level stuff, and then there's the I just am making another one of the thing that the greats already figured out.
Pointing our fingers at Hearthstone or
exactly. And this is not a bad thing, by the way, because that's what the industry runs on, right? You can't have not every game can be a completely new experience. And not only that, but it would be a problem if it was, because someone who wants more Magic the Gathering has to be able to go buy something like Magic the Gathering, right? And that is what Hearthstone is providing, or something, right? Like, you know what I mean?
Are you a Magic the Gathering enjoyer? Do you have some favorite games that you play?
No, I am not really knowledgeable about collectible card games. I think this is part of when I say I am bad at game design. Part of being bad at game design is also not being very intuitive or, familiar with the kinds of games that are seminal, right? So, I mean, I do know how to play Magic the Gathering, but if you asked me to like make something new in the style of Magic the Gathering, I probably couldn't do it, right? So, I mean, that's just kind of how it is. But to finish answering your question, so when we say game designer in the game industry, and we're putting that as a title, as like we're going to hire a game designer for a team that has many game designers. We are Guerrilla Games, and we're hiring for the next Horizon title, and we want a game designer, or it's a game design position. They're usually talking about things like quest design, placing things in levels, figuring out how much the items cost and where those items will go, managing script files that say what happens when you talk to this character, right? That's like what a game designer is doing.
Got it.
They are not fundamentally coming up with a new game design because, if you've ever played the Horizon series, they are literally just the same game as you have played before. It's a standard AAA RPG model with like no deviations, right? And so those are two different activities, and typically you won't see them intermix that much. Typically a project is either something that's trying something really new, in which case it's probably not AAA, because no one's going to spend $500 million on something that people might not like, right?
Yeah.
And similarly, if you're somebody who's like a small team, we want to do this kind of new idea that we're exploring, it doesn't make a whole lot of sense for you to have some $500 million team behind you, because what are they doing? They have nothing to do while you're exploring that concept and figuring it out. So it wouldn't really even make sense. Like at most you could have, and this has happened in the industry certainly, you could have prototyping teams inside AAA studios that were working on that, and then it will bubble up, right? But nobody is sitting down and going like, we're going to like have an exploratory process for the game design of this thing that's going to cost us $500 million to produce. So that's the best kind of explanation I can give of that spectrum there. And I am not good at any of those things, right? I don't have any of that skill set. I could probably learn the one that's like get hired as a game designer, maybe, if I worked at it. But I definitely can't do the other one, which is like pioneer a new thing.
Yeah. It's like the greenfield stuff where you're like really coming up with a game from scratch. It sounds like is either like you're doing your own indie game, or maybe you're working in like you said, a prototyping,
an incubation style thing. Yeah. And that exists. Like big studios will do things like that to try and find new things they can integrate in, right?
Right. Yeah, that makes sense. Okay, so then my next question is more along the development side, which of course is your wheelhouse. In the web development world, which is where I come from, we've got titles like backend developer, front-end developer, DevOps engineer, and there's kind of different skill sets that you learn under those titles. I know nothing about gaming. I only ever hear the title game developer, but I have to imagine like there's a whole lot of different skills that go into making a game, especially if it 2D games, 3D games, online games, local games. Like, what are the different ways that people should think about like the actual careers that exist for game developers?
Well, I'm sadly probably a bad one to give a good answer to this question, because really I don't work in the hiring pipeline or have that much exposure to it in a modern AAA studio. What it looks like from that perspective changes over time. What I can say is, from a point of view of skill set, like what you need to understand, I would say that game development typically breaks down into sort of generic roles and specialized roles. The generic roles are more like web development.
Okay.
So in other words, they would be things that a web developer would recognize. You are responsible for making the front end GUI thing. You don't handle the rendering of that or anything like that, or the user input or anything, but you are laying out like, button layouts, and when things click, you figure out what happens, that sort of stuff. You could have things like that. You can have a backend developer, just like you have in web development. We're collecting player stats. We're handling live patching. We're, even in DevOps. I mean, games, these huge AAA games have multi-terabyte source storage, right, of their assets and code. And you need DevOps people, I think is the term generally or IT people,
or like
whatever
cloud engineers,
cloud engineers, build managers, whatever the right term is in web dev. There's an equivalent thing going on. Like all those same things have to happen. Then there are game specialized roles, and those tend to be usually centered around AI, physics, or rendering, sometimes sound. And those are people who have special knowledge of how that kind of code works. Rendering and physics are the biggest. They are incredibly important to games, and they require very specialized knowledge. A person who just knows how to program will have no idea how to approach that kind of code at all, right?
Yeah. And it's not just the code, I imagine. It's the math and like the computer science that goes into the algorithms, and I'm assuming it's a lot of matrix math and maybe even hardware stuff, like understanding how the GPU will interact with the code.
Correct. So you need to know just a wide array of things. You need to have a really good understanding. I mean, have to.
Yeah.
There's good and bad of each of these types of programmers. So,
right.
A good rendering programmer, for example, has to know just a tremendous number of things that an ordinary programmer simply doesn't know. And those things are not very easy to acquire. It's not like, it's just this API, I need to learn how to use a Docker container. So I went and read the documentation for a Docker container and now I can use it, right? It's like, it's a series of APIs. It's an explanation of how it works and I'm done, right? It's like, no, it's like, okay, you need to understand probability and statistics because you need to be able to understand like what Monte Carlo sampling is and how, Markov chains work, or at least, right? You need to be able to understand all of the linear algebra because you need to be able to do all of the 3D computations. Maybe you need geometric algebra, depending on whether you're doing it in 3D or higher, like how you're doing your notation, right? Rotations are often handled in 4 dimensions for various reasons. So you got all these special purpose pieces of knowledge. And then you have to know all the hardware correctly. You need to understand what SIMD looks like. You need to understand what SIMT is, and you need to understand how shader compilers work. You need to understand how the PCI bus works and how it transfers data, what memory mapped IO is, all that sort of stuff. You need all of those things to be a good rendering programmer. Now, you can have a subset of them. There might be someone, for example, on a large rendering team whose only job is there to make the reference ground truth rasterizer, something that basically does a equivalent of like an offline Pixar style render that the rest of the team can use to tell whether their real-time render is getting the correct lighting results. You may have no idea how like that is happening at a hardware level, and that's okay because that's not shipping to the customer, right?
Right.
So there's ways you can have subsets of this knowledge and still be very valuable to a team. So I don't mean to imply that a individual rendering expert has to actually know every single one of these sorts of things to be a contributor. Absolutely not.
Right.
If you were the only person, you probably do. But if you've got a team of 5 or 6 people or 10 people or more, then they can be specialized in just one of these things, and that would be very helpful to that team. In fact, even possibly preferable, because you just say, okay, that person does this, and then no one else on the team really has to understand how these sampling theories work, and then we move on, right?
Nothing's more frustrating to me than hearing someone say, as a programmer, I don't need to know about X. I don't know. Let's take a classic one. Like, I don't need to know about binary trees. I'm a programmer. I've never used binary trees in my life. And then you like find out that they're working on a WordPress shop for like a local e-commerce store. And it's there's just so many jobs out there for like programmers, and it's too generic of a term.
Sure.
I'd be lost. Like, I'd be lost in game development. I'm lost. I knew like 95% of the words that you said, but like I don't understand almost any of the underlying principles that I'm sure would be requisite or at least very helpful to be a rendering engineer.
Well, and it probably would have been a waste of your time to know them is the other thing, right? Because while it does help sometimes, there's a tremendous amount of value in learning something about how other people do things, because you may be able to import some of that knowledge into, what you're doing. I want to say that there are some classic examples of this in backend dev. For example, I want to say that it might have been Eric Veach who designed Google's original ad pricing backend, the way that it worked. And he's the person who invented Metropolis Light Transport, which is a foundational paper in rendering. And so knowing things like how these sampling theories work, you might then go, oh, wait, we can apply this to this completely other domain that's critical to some web company. So that is great. And I would never want to discourage someone from doing it. But on the other hand, it's undeniable that if you spent 10 hours a week reading SIGGRAPH papers, you would have a tremendous amount of knowledge that you simply cannot use at all, right? Because the vast majority of it, right, you're hunting for a diamond in the rough at that point, which, again, I would never discourage someone from doing it. But do we need the vast majority of programmers to really know, about this particular algorithm that someone was using for path tracing? No, we don't. Having one person who knows about that, who works in web dev, is enough. They'll let us know if we need to go know this thing. So, I wouldn't want to overstate the case for cross-disciplinary learning either.
So one of the reasons I'm so excited to have you on and talk to you is you've got this website project, I guess, Computer Enhance, right? Educational project. And I love talking about this idea between, or this contrast between stuff that you should study with some career goal in mind, or maybe not even a career goal, but project goal in mind, and just-in-time learning. Because I don't think everything fits neatly into either box. I do think that some stuff is better learned up front. It'll just take too long if you try to learn it all just in time. But on the other hand, if you try to learn everything up front, like you just said, you could spend weeks learning stuff that it's highly unlikely you'll ever use it. How do you approach this idea of what you're going to teach to people up front in a general sense versus stuff that you think they should be looking up on an as needed basis?
Well, Computer Enhance specifically was sort of an experiment to test the waters to see whether or not people would pay for learning materials about, for lack of a better term, fairly serious programming, right? This stuff is not really for the faint of heart. It's not learn JavaScript for front-end development in 21 days kind of stuff.
Yeah.
And so it's to see is it worth putting time into this, and to see if that goes. And as such, what I did was I selected what I thought was something that was something I think every programmer should know, and that most programmers don't know. And that is how their code runs. Okay. Most programmers have no idea how their code runs at all.
Do you just mean on the hardware, how the CPU works?
They have literally no idea. They can't read assembly language, for example.
Yeah.
So they don't know what the machine is actually going to do. And as a result, the real downside, I think, of this, the very severe downside that we are experiencing in the world, is that code runs massively slower than it should. And it's one thing to have code that runs very slow and you know that. It's another thing to have code that runs very slow and you have no idea that that's actually true. For all you know, this is as fast as it goes, right?
You made the trade-off versus... I guess it's you meant to make the trade-off versus I guess you made the trade-off.
Or not. There might be no trade-off.
Yeah,
there might be no trade. You just literally wrote something very slow, and there was no real trade-off to make, right? You didn't gain anything. You just made very slow code.
It could have been fast for the same amount of effort.
It could have been fast for the very same amount of effort if you just changed the order in which you did two things, or something like this, or thought of this a slightly different way. The same amount of typing would have got you massively faster code, right?
Right.
And so the reason that I think, and just to tie it back to your question or point, I guess I would say, that you made about just-in-time learning versus sort of learning up front. The reason I think this is so critical for learning up front is because it's a knowing what you don't know kind of thing. That's how I would differentiate between those two things. Just-in-time learning is great for anything where you will know when you need to know it. Because anytime, that's what's so great about the internet.
I love that, yeah.
Right? Anything that I know I need to know, when I need to know it, the internet solves my problem. I go to Google, the Docker container. I go to something, it's in order to deploy this to this web service, fly.io, you need to build it as a Docker container. I don't really need to know anything about Docker containers prior to that. I know, okay,
Right.
I need to build a Docker container for this deployment. I will go learn about Docker containers now because it is relevant to my thing that I'm doing, and now I'll learn it. There would have been no benefit for me learning it before because I never would have had to put something in a Docker container, or I should say Docker image, before, because I would have been deploying anything as a Docker container. That kind of thing I think is appropriate for just-in-time. And I think that web developers probably have a skewed sense of just-in-time because, if I may, most web things are best learned just-in-time. They are typically transient, artificial pieces of knowledge, such as how a Docker container works. When later people replace Docker with something else and we don't use Docker anymore, there will be literally no benefit to knowing specifics of Docker. It's not a foundational technology. It doesn't reflect how hardware works. It's not endemic to any particular thing. So the only reason to know it, kind of like the only reason to know JavaScript, the only reason to understand the DOM, the only reason is if you're doing that exact thing at that exact time. There's no other reason to know them. So I think they have a skewed sense of just-in-time, but that sense is correct for their domain, right? There would not have been a benefit in their true experience as programmers of learning these things ahead of time, because if you spend all your time, I mean, I'm not going to be able to pull an example, but you probably could, where it's like this JavaScript framework, if you spend all your time learning it, and then all the time, suddenly you realize, oh, this whole project's going to be on a different framework. So all that knowledge is useless, right? It's completely useless. You don't need it for anything.
I've spent a lot of time. Well, I shouldn't say a lot. I've spent some time in React, but like these days I just program in Vue, and some of it transfers, but by and large, it's just syntax anyways, right? So
exactly. So I think things like how modern CPUs work, there's a lot of very durable concepts in them. A lot of them date back to like the 70s or 80s, and they're not going away. They're just how code runs, and they're kind of underpinned by fundamental aspects of technology and physics that mean you probably just should know this, because it is how all of your code will run, not just now, but probably forever. And the only thing that will really change is we'll be adding things. Now, forever is the wrong term. Obviously, someday maybe we have quantum computing or something and changes everything.
Yeah.
But for decades, this has been how things have run. And for decades more, these concepts will probably be durable. And there is no way for you to know you don't know them. There's no way for you to know when you're programming that you don't know, right, what SIMD is. You will have no way of knowing that a piece of code that you're writing could have been massively faster if it was vectorized if you don't know what vectorization is. There's nothing, It's not like a Docker container where you are literally hitting a wall where somebody says this has to be in a Docker
where
container.
You hit the function call that's like SIMD, right? Like you're not, okay.
So it's very easy to think that like, oh, this thing must just be for games, or this thing must just be for something else because, I don't know, I haven't seen the API call that's like, prefetch this into the cache or whatever. It's like, but these things are true. And if you know them, they affect all of your decision-making. They affect your decision-making all the way up the chain to when you're typing in code in JavaScript, because if you know what that will actually translate into after V8 gets done with it, or whatever you're running it through at this particular point in time, you're like, oh, this was a bad idea, what I'm about to do. I should do it this other way because my code will run massively faster. That's the thing I would like to give people with this series, is knowing what they didn't know before. So then it's all in their heads and they can recall like, oh, wait, I should probably think about this aspect of computing that I wasn't thinking about before because now I've been exposed to it and I've seen it once, right?
So first I'll say, like, I'm a big fan of this idea. So I want everyone who's listening to this pod, if you're interested in learning this type of stuff that Casey's talking about, go check out Computer Enhance. I do want to play a little bit of devil's advocate, though, because it's fun.
Go ahead, yes.
So specifically with JavaScript, for example, I'm not a big JavaScript fan. I write a lot of Go on the back end. I've been enjoying Go. But let's take JavaScript because it's a better example. There's more layers of abstraction involved. So like you write some JavaScript. Sometimes it runs in the browser. Sometimes it runs on a node server. Sometimes it runs on a bun server. You understand how computer architecture and hardware works, maybe on your given workstation, right? Like, let's say you're working on an M1 Mac. You have like a good understanding of ARM assembly and like whatever low-level internals that entails. are there just too many layers of abstraction because you happen to be working in JavaScript between your JavaScript and the CPU for it to have a direct impact on the code you're actually writing? Or do you think that there is like a day-to-day benefit from understanding like at the hardware level?
So I guess I would say I'll say a few things about that.
Yeah.
Because there are many ways. So the first way is JavaScript is probably a bad example for what you were trying to illustrate, because the answer is absolutely. JavaScript translates almost directly into assembly language code most of the time because it is JITted in almost every environment where it's run. So a better example might be something like Python, where it is like literally Python takes, one of the very first things you'll see if you go to Computer Enhance and take that course, the performance-aware programming course. One of the first things I do is show you how many actual assembly language instructions it takes to do an addition in C, which is one instruction, and how many it takes to do it in Python, which is over 100.
I was going to say, I don't want to know. Don't tell me.
So Python's a better example, because if you're running interpreted Python as opposed to running it through some kind of a post process, there are ways you can get your Python to be compiled, for example, right?
Yeah.
Then that's kind of probably a better example of what you're talking about, where you're like, can a Python programmer really benefit from understanding these things? So let me tackle that, because I think that's the harder question for the person responding to that's a harder question for the devil to ask than the one you asked, which is like, yes, literally JavaScript translates directly to assembly and you can trivially see the mapping, right?
Cool. Yeah. Let's do the Python one then.
So we'll do the Python one because that's harder, right?
Yeah.
But in my opinion, it's still actually pretty easy. So in Python, for example, if you don't know how expensive it is to add two numbers together, not only do you not realize that your Python code that's doing arithmetic is up to 100, at minimum 100 times slower. It actually gets way worse when you factor in vectorization and multi-threading. But so we'll put those aside, but at least 100 times slower because of the interpreter. So you don't know that. So you write math code, you're like, I don't understand why this is so slow, or maybe this is just how fast it is, it goes, right?
Yeah.
That's a problem because you have no idea how fast the code could run. If you'd learned how machines work, you would know that it was massively slow. But also, it makes it incredibly hard for you to have any idea what you're doing when you then want to use the things that people are telling you to use to make the code run faster. One of the things I was told multiple times by people who commented on my Computer Enhanced stuff is they're like, I totally get like what NumPy is about now. Like why I have to do these weird things and what order I might want to do them in. Because now I get it. I have to offload addition to C code, because if I had it in Python code, it'd be too slow.
Right.
So I need to put it in these bulk batches that I can get over to someone else to do the math for me, right? And they can start to build up an understanding of like what they might actually need for libraries and where those library call points should be in their code, what they should be aiming to offload, because it's intuitive now. And so you can even make performance improvements in your Python code even without doing something like Python, by just understanding this, because now you get it. Like, oh, okay, that's going to be this. I'm going to have to offload that. I understand why I have to offload that, because I'm trying to get someone to do this at less than a cycle per add instead of 100 cycles plus per add, right? Right. So that's the kind of thing that I think it makes such a dramatic difference. And again, I think it's not that hard. It's not that hard for people to gain that understanding and then go right back to programming in Python. But now you also have an additional trick up your sleeve. If you are doing something that is computationally intensive, you can't find a library that does that thing. It does not take very long, and I show this in the course. Drop it into Python. One little routine in Python, you do your bulk computation there the way you wanted, and suddenly it's back to one instruction per add again, which is, by the way, modern CPUs do more than one add per cycle. So it's actually like you get even more performance than, it's not one cycle per instruction, right, anymore. So again, many, many reasons why I think people should understand this, because they then, once they know the true boundaries of what's possible, they know when they're nowhere near them. And they can say, I should go do something to push my software up into that range of reasonable performance, because wow, what a difference it will make to my customers. Instead of waiting around for seconds or minutes, they're getting results instantly, right? And that's really what does happen when you make these kind of improvements.
Okay, I think this is going to set the tone for the rest of the conversation, which I'm super excited about because we haven't had an episode like this ever, probably. So this will be fun. So I want to talk about, you mentioned how you have all these thoughts and ideas, and this might be what you're more famous for online, about how like software is getting slower, bloatier, less performance. Can you give some specific examples?
Sure. And I guess there are many examples, so I'll pick one that happens to be recorded by me in a way that's very easy to see, but it may not be the best one for your purposes, so I'm happy to go through other examples. It's a podcast, so I'm trying to tell an interesting anecdote, right?
Great.
So in the old days, in, say, circa the year 2004 or something like that, quite some time ago, 2 decades now, if you were to load Visual Studio, Microsoft's dev environment, which we all used as the debugger. We didn't necessarily use it as the editor, but in those days we used it as a debugger, and many people did use it as their editor, as an IDE, either way. Mm-hmm. It loaded pretty much instantly. You know, it wasn't maybe as fast as it could have been, but it was very quick. You could load projects to debug, and they loaded pretty much instantly. And when you stepped through the code, the watch window updated instantly. You hit step, and the value's immediately there. You fast forward to today. Well, I'll include the anecdote. Fast forward to 2017, and I was talking about this on a live stream, and someone from the developer studio team actually contacted me, and they're like, "We'd like you to give feedback on the program." And one of the things in this little feedback questionnaire they sent me was, how long should it take to load a project in Visual Studio? And the smallest number, the minimum you could pick, was less than 10 seconds.
Oh, no.
So the only number they could conceive of as being low was like 10 seconds. They're like, well, if it's less than that, then why would it, right?
I never experienced that, by the way. I never experienced Visual Studio loading instantly. I think the first version of Visual Studio I was on was like 2011 or 2013. And it's always been a hell to open.
Yes. And the debugger has been similarly incredibly slow. The reason I brought this one up as a simple example is because it's not really doing it like the excuse most people use is, well, I'm sure it's got way more features now than it used to have, with no explanation of why features in the program would change the speed at which an integer can be displayed in the watch window, right? Which says to me, again, motivation for computer enhance. It says to me that modern programmers have no idea how various aspects of a program affects other aspects. To them, more features just means everything is slower. Like if I add a feature to the editor in Visual Studio, it means that the watch window goes from being instantaneous to taking several seconds to like update.
Right.
I have no idea how a programmer gets there in their head, but that is what they think. And I'm trying to counteract that. But back to the point. The reason I picked that anecdote is there is a video of me online where I went back and I recorded this so that people don't have to believe me. I took a machine from 2004. I show the stats of that machine. It is embarrassing. It's something that could not even load like a modern program. Right?
Google Chrome probably can't load on it. Yeah.
And I show the same project and the same files loading and stepping through the watch window on both of them. And people could not wrap their head around it. They were like, there must be something else. Like, no, there's nothing else. It's just bad code. It's bad programming practices make slow code. There isn't something else. It was a million really bad decisions that now are almost impossible to speed up. Which tees up another point if you want to get to it later in the podcast, which is the idea that performance is about hotspots. But you could put that in your quiver if you want to.
I definitely want to ask about that.
Okay.
Because that sounds very interesting, and I don't think I'll get another chance. So
anyway, I'm happy to go through other examples. I don't know if that example was the kind of thing you were looking for, but that was the first thing that came to mind, that people can easily go watch me demonstrating on a video so that they know what I'm talking about.
No, so that's a great example. So Microsoft Visual Studio, to be clear, we're not talking about Visual Studio Code that a lot of listeners might also be familiar with. This is Microsoft Visual, and it is like, I mean, load it up on your computer. I believe today it is still extremely slow. Last time I tried it, I think it took about 20 minutes on my machine. Or it's 20 seconds on my machine.
It's very slow, yes.
It's open a very simple project.
And to hit more to home too, like Microsoft Teams recently went through a thing where they're like, we completely rewrote this thing or partially rewrote this thing to massively speed up the boot time of Teams. And they're like, we got it down from 20 seconds to 10 seconds or something like that. And again, you're just like, it's a chat client, right?
Either way, I'm getting up to get a coffee. Like,
yes, and people, again, the excuse parade comes out and they're like, I'm sure it was just checking credentials or whatever. It's like, that cache this stuff. Like, that is how that works. Like, let the user start interacting if you really... And plus, why did it take 10 seconds to check credentials? What is going on there? Modern internet is like millisecond ping times. Like, even if you were talking about something where you were intentionally taking a long time to salt and decrypt a password, that should have been a progress bar. So I'm pretty sure that is not what was happening, right? If it's really that kind of a thing. We're talking about something very different, which is probably a bunch of serial dependency chain server round trips that are just taking this long because no one actually thought about how it should start up, and off you go. Anyway.
It's a fantastic example. So what the underlying problem, like so far we've talked about like, well, programmers either aren't taught or maybe aren't given time or don't care. I guess, let me just ask you, like, what do you believe the primary driver is for a proliferation of slow software? Is it just lack of education? Is it lack of caring? Is it business people?
It's lack of education or lack of culture, you might say. So saying lack of caring suggests that people were taught this or taught that it was good or that the culture believes it's good, but then they themselves are personally deciding not to care. But I don't think that's the case. I'm sure that would be the case for some, but probably very few programmers, right? Just people who are just lazy and don't care. And that's fine, right? There's going to be some number. But is that the majority? I don't think so. The reason I don't think so is because if you look at what it is culturally acceptable in programming to care about, such as knowing how a Docker container works, knowing how React.js works, programmers eat that stuff up. Those things are at least as complicated as learning how a CPU works. These are massive API sets with tons of gotchas and weird behind, and people love here's insider tips on how to, do this thing in Docker that you didn't think you could do. I mean, an example I've used on a podcast before was I was like, if you can learn how CSS works and actually successfully get a page layout looking halfway decent in CSS, you can learn assembly language. It's easier to understand. It's less complex. There are less special cases. And so the idea that programmers are too lazy or something to learn and employ this stuff, I think is simply false. It is that culturally they have been taught and are working with peers who think that somehow it's virtuous to not know how a computer works. And that is the problem. Every person who programs for a living should know how a computer works and care whether the thing that they're shipping is living up to some reasonable percentage of the performance of the hardware that they're given. It doesn't have to go all the way and shouldn't go all the way because there's diminishing returns in terms of effort that you're going to put into it. But in terms of just wasteful squandering of computation power, that should have culturally gone away a long time ago, but regretfully, it is still with us today. So I think it is 100% a culture education problem, however you want to put that down, not a problem with engineers themselves individually deciding to be bad actors.
I like that. What are like the top 3, let's say like kind of broad concepts, pick between 1 and 3, that you think should be taught in this like non-just-in-time way? So just, 3 things that like people should know. I guess you already gave one great example, right? People should know how their code runs on their hardware, which I guess like when you get down to the specifics, do you just mean like assembly language?
Yeah, so I would say if it were up to me, every programmer should know how to read basic assembly language instructions. Read, not write. And I want to be very clear on that. People like me, we don't really write assembly language hardly ever. For testing, sometimes, or to figure out why there's a problem with something, we might. And very occasionally, if there's really some super important thing, maybe someone will write some assembly language. But by and large, when we talk about this kind of programming literacy, we're actually not talking about writing assembly language, we're talking about reading it. Because most CPUs nowadays and most compilers can be coaxed into a position where they simply will do a fairly good job of executing code without you having to get in there and specify it. So there's a misconception that comes from a long time ago. It's what it was true in the past, so it's not erroneous, but it is no longer really the case, that getting any kind of reasonable performance out of a computer meant hand coding things in assembly. That is simply false. It isn't. It is almost never done nowadays.
It's like your famous roller coaster tycoon, right?
Yes. That is almost never necessary. And to the extent that it is necessary, you're talking about very specific kernel, like not kernel, the operating system, but like little nugget routines that make a huge difference to something somewhere like video codec, right? Where it's just plowing through and we want it to be as fast as possible. Okay. But most code, no one is doing that, right? So when I say assembly language, I mean reading it. Being able to read basic ARM or basic x64 assembly language to the point that you understand the kinds of operations that the CPU does. Then, understanding the CPU's execution model for those things and the basic speeds at which each of those things happen, right?
I'm a big fan of this. I mean, in the web world, I talk about like, you should have a really good heuristic for like how long it takes to go to the database versus to disk versus to RAM. This is like that at an even lower level, right?
Yes, it's the exact same thing. It's basically just saying every programmer should have, like a doctor, a lawyer. They have continuing ed credits they have to get. They have to go to like seminars and prove that they were still like, in my world, it'd be like programmers have to keep their knowledge up to date at roughly what is going on inside the computer. You don't have to be a master. You don't have to be Agner Fogg and like be doing all kinds of crazy tests to figure out exactly how the iCache or the UOP cache is read, how many things it can feed from there to the back end in one site. Like, okay, that's full-on hardcore optimization land, and you don't have to go there. But just understanding basically, this is what a CPU will do on one cycle. This is what it will kind of do. Just getting that pipeline understanding. Here is how fast an L1, L2, L3, and main memory are. Here is how fast an SSD transfer is. Just that is, I think, something everyone should know. And that way, when they write a piece of code, they can go, wait a minute, this is doing like only, 2 milliseconds worth of operation, but it's taking like 5 seconds. Like, what happened, right? And there's two benefits to this. One is now that programmer knows that they should be doing things differently. Find another library, find out what's wrong with your VM, find out what happened, like look into it, right? But the second thing is, the more you do that, the less you have to do it. Because if every JavaScript programmer got pissed off when something was going too slowly, then the backends and the API surfaces would all get better because no one will put up with it, right?
Right.
So it pays dividends as well, right? Whereas if everyone's just happy with everything running super slowly, then the backends get slower, or they stagnate, or they don't they don't modify Python to fix the problems with it that make it hard to compile. They don't fix JavaScript's problems. They don't fix whatever, right? So the more people who are aware of this, the less structural decay there is as well, because people wouldn't put up with it.
Okay, so just to give you a little bit of context, BootDev is this program for learning backend development, and I say the reason I named it BootDev was to be a little tongue-in-cheek, because I too was very frustrated with like, hey, learn JavaScript in 2 months and get a great job making six figures.
Right.
At least I'm assuming that's part of your frustration, is like this idea about like, we're going to learn extremely surface level stuff and then we'll be able to ship and have amazing careers.
Yeah.
I think it's going to take a little bit longer. The course that I keep putting off, that I have not yet added to the BootDev curriculum, which at the moment is about 26 courses and projects, is a course on assembly. It's one that I've wanted to put in yet, but have not yet decided what to do. And so now I'm just going to like pick your brain. Do you need to know ARM and x86? Would you only teach one? Is it like is it the concept of how the CPU is working that matters more than understanding the syntax of a given assembly language?
Yeah, I mean, assembly language is really simple enough that even the question doesn't even really matter that much. Right. It's like you would be learning some specifics of a particular ISA, but those specifics are not really going to matter unless you're analyzing that particular ISA. So from the standpoint of the literacy, learning how to read learning how to read 6502 assembly language is sufficient, because once you can read any assembly language, once you can read one assembly language, you understand the concept of reading assembly language. So then, if you want to know how a particular thing is working, you are on Godbolt or something, and you put something in and you see some assembly on the side, but it's for ARM and you've never programmed ARM, so you're like, what the heck is this? It's just trivial. You look up what those instructions mean in the manual. And it's the same as you've done JavaScript front-end programming and someone comes along with a different front-end framework. You're not like, oh my God, what do I do? You're like, no, I've done this. I've learned a front-end before. I just go learn what the various things are that I'm going to have to learn in this front-end, and I'm done. Same is true of assembly language, right? And so there are ISA-specific aspects that maybe you could say, if you were trying to educate someone about a particular type of assembly language, might be kind of important, like memory semantics or things like that. But as long as you make people aware that those exist, again, they can just read those. So in terms of the literacy, any assembly language will do.
I worked, so my first job was such an interesting job. I was working pretty close to hardware, and I had to read like spec sheets for chips. And the thing that was so interesting to me about it was, first of all, I was like thrown into this stuff and did not have a mentor. So I was like trying to figure stuff out on my own as like the lone programmer amidst a bunch of like electrical engineers and mechanical.
Okay.
And the thing that was so interesting to me was when I realized like this stuff seems super scary and complex, because I'm looking at like physical papers with like, you know, here's a byte, and it's like the byte of data is literally like drawn out on the piece of paper, like 0111000, and it like has an arrow and it points to like some operation. So it looks like super scary. But when like once you realize that it is just a lookup, like a physical lookup on a piece of paper, like I don't have to memorize this stuff. All I really needed to know was like what a byte of data is, what ones and zeros are. And like once I know that, I have this little reference manual. Like, okay, I just need to set like this part of memory to that byte, and then this thing will happen, and the hardware says it will, and oh look, it did that thing. Like, it's tedious, it's weird, but it's actually not that. It's not like I needed to know calculus to do it, I guess, is like what I'm trying to say.
Well, and as I think I tried to say earlier in the program, it's easier than things you have been doing. The complexity of hardware by necessity simply doesn't get to the same point as whatever your favorite JavaScript library is. They simply can't afford that kind of complexity inside a chip because it wouldn't perform very well. So as a result, the kinds of things you will be asked to learn. So once you can read assembly, we'll talk about the next step. Once you can read assembly, understand basically how the computer processes those instructions to get things to happen in your computer's memory. That's what a computer basically does, right? That next step is pretty simple compared to how does the browser lay out a web page. The knowledge necessary to correctly predict what the browser will do when given an arbitrary stream of HTML5. I mean, I would argue there is no human today who could even do it. I don't think there is. Like, it's so complicated with so many lookup rules and so many special cases and so many interacting elements and so many different caveats, not to mention things that might even be implementation defined details. Like, I don't know how actually rigorous HTML5 is if you really got down to it. When you compare that versus even x64, which is a fairly complicated instruction set, it's really just not that complicated. It only does a very small set of things. And when you further restrict that to the actual set of instructions your compiler might ever actually output, it's like a handful of instructions. There's hardly any, right? Yeah. So understanding what those do, they're all primitive. They're like, add this thing to another thing, XOR this thing with another thing. It's that's it. Understanding that is so much simpler than what you've been doing. That's what I always try to tell people. Like, it's so much simpler because it has to be. It can't be that complicated.
Well, I think it can be counterintuitive. Like, the simpler tools you're given with, right? And, or, add, subtract. You can build crazy complex systems on top of that by combining them in interesting ways. But once you start adding like very specific APIs, and we'll call it like a wide and specific API, you are artificially limiting what you can do with it, if not explicitly, implicitly, because you're encouraging certain things through the use of the API. Like you could make the argument, for example, that when you're constrained to React, even if you could drop down into lower level JavaScript, right, and do things outside of what the library inherently supports. Maybe React Native is a better example of this, because like you're working within React Native, or you like drop down into like Java. You're encouraged not to, and so you don't, right? You like play within the rules of the sandbox that you've been given.
All I'm trying to say in terms of analogy, let's say, is just that if you can understand how the API of React behaves, you can read assembly language and understand what it does. Full stop.
Just because it's easier.
Way easier. Not even slightly easier, but massively easier. Because literally the things that you need to understand are like, this will add two numbers together. That's like the level of complexity that the CPU can do something at. So understanding how to read and know what that's doing is so much simpler than like, what will the lifetime be of this React thing, and how will it interact with this other kind of button that I'm going to create? Or when will, it's for some reason this slide out panel isn't working and I don't know why. There's none of that in assembly language. It's like literally it just does one add, and you can literally step through it in debugger and see it do the add, and that's all it can do. It has no other things that it can do. They can't be complicated. They can't really have those kind of interactions. And so it's so much simpler than what people are used to. That's why I say, like, don't be afraid of reading assembly language. And we teach it. It's very simple at Computer Enhance. I've got another thing I'm going to be doing soon that's another approach to teaching assembly language. So I think everyone can learn it, and should, because it demystifies computing a lot.
No, that's awesome. Sorry, my point was like related. It was not the same point.
Okay.
I agree. Assembly language is much simpler. Like, my point was that it kind of has to be, because when you add complexity, you actually restrict what you can do. In a way, that makes sense. Unless you, of course, drop back down to the primitives, in which case you can do lots of things.
Well, in a way, yes, but in a way, no, right? Because let's take something, for example, like a NAND gate, right?
Mm-hmm.
In theory, if I remember my not really existent computer engineering knowledge, you can build anything with a NAND gate. Like an entire computer
That's
can
not and, right?
Yeah.
For the listeners.
I believe like just some number of these gates can build any circuit you want, right? Like any digital circuit. That's just how it works. Yeah. If you think about that and you ask the question, how hard is it to understand this billion transistor diagram of NANDs versus how hard was it to understand NAND? The answer is it's trivial to understand NAND and impossible to do the 1 billion. I would argue that's like React versus assembly language. Assembly language is the NAND gate. React is the billion transistor thing someone made out of NAND gates. Understanding how React works is like either difficult or almost impossible. Most people probably only understand vaguely what will happen when each API call occurs, and only experts in it probably know all the actual real specific things that might happen given any arbitrary set of React calls that could interact with each other, right? So when you build up things out of smaller primitives, the thing that you build up is actually way harder, even though it may be less capable just because of that. Is that what you were getting at? I'm not sure, but that's what I would...
You know, it turns out, after hearing how confused I've made you about my point, it's possible it was just a bad point.
Okay, that's fine too.
But I can share a related anecdote that also, at least in my convoluted explanation of what I'm trying to get across, made sense.
Okay.
Just last week. So on boot dev, we have Go in the backend running on our servers, and we use Nuxt as like our rendering server. It's basically just a front end, but it does run on a server specifically for like SEO purposes, right?
So I'm not familiar what is Nuxt. I know what Go is, obviously, but I don't think I know what Nuxt is, since that's not, remember, I don't work in this domain. So you know,
do you know
there
Next
are some set of words I will know, and some set are like, what is that package? Okay.
Yeah. Do you know Next.js?
No.
Okay, so but you know React. So React is like the front end framework. Some people call it a library. I take issue with that. I call it a framework. The front end framework rendering stuff in the browser, but it runs completely in your browser. Next.js is essentially a meta framework for React that will allow you to do that rendering on a backend server. And then it like hydrates it to the front end. So if you're doing like SEO stuff, if you want your page to be crawlable, then you'd use something like Next.js. Nuxt.js, very confusingly named, is basically the same thing, but for the Vue framework rather than React.
Okay, so this is basically like when the mama bird pre-digests the food for baby bird and regurgitates it into baby bird's mouth. So it's already kind of been pre-worked, right? Like you don't have to run all that JavaScript stuff on your side. It'll just come through as raw rendered HTML with presumably enough JavaScript left over to handle dynamic events or something.
Yeah, and this is like the issue I'm getting to is there's a lot of magic baked in, basically.
I'm sure.
For example, so our Nuxt rendering server runs on the edge, which means it's geographically close to the user. So we kind of treat it like a client in that way. And then our server is like a traditional web server running in our data center. And it's like a JSON API. The Nuxt server will go get some like JSON from our like central server, right? It's got like your user account data, stuff like that. And then it will render on the back end the HTML. And it will also send the same data in the same payload as JSON. So you've got the data twice, like once serialized to HTML, also, and then also in JSON back to the browser. So the browser can then like render the HTML as it is, and it has the data in JavaScript form to do like dynamic stuff with it on the front end.
I see.
It's actually pretty cool, but it's really magical, not very performant, and the APIs that you're given, it's unclear like what is going on under the hood. Right. And me and a couple other developers who, we write a lot of Go, we'd been doing all of this stuff in Nuxt for like over a year, and it had been performing a consistent way. But it had only been performing that way because we happen to have an interesting convention about how we write our functions by using guard clauses, basically. And anyways, long story short, we onboarded a new engineer, Sarah, who's amazing, and actually dug into the docs and found out what was going on. And our explanation of the convention that we were using was just wrong. Like, it was just outright wrong based on a complete misunderstanding. Happened to work in like basically all scenarios. But the reason we found out was because she wrote some code that we wouldn't have written. And so in a pull request, I was like, this is weird. Like, I don't think this will work. And she's like, why wouldn't it work? Of course it would work. Like, this is how Nuxt works. And I'm like, I don't think that's how Nuxt works. Right. And upon further inspection, I just don't know how Nuxt works. So,
which is easy to do, right? Because it's like these things are massively complicated for what they do. So it's just like, it's easy to not know a specific because there's so much internal plumbing, right?
Yes. Oh God, there's so much internal plumbing. So anyways, long story short, I agree with you. I think this is very cool. And I actually want to dig more into computer hands myself because I could use the refresher. It's been a long time since I did anything with assembly language. So you've got this video about the 30 million line problem. Can you give us a quick overview of what the problem is?
Sure. So it's an inappropriately named talk because if we're talking about it here in 2024, it is no longer the 30 million line problem. It's more like the 100+ million line problem because programmers only add lines these days. They never remove them. But what that number came from when I was giving that particular talk was originally a talk I gave internally to people at Intel. But then I put I haven't really ever professionally recorded it. I literally just have it when I gave it on a live stream impromptu one time. So I was like, it came up. So I've never really recorded it that way, but it nonetheless has been very widely watched. And I get lots of comments about it from people as well. Where that number comes from is my rough approximation at that time, which was 2015 or something like that, when I originally gave the talk at Intel. It was my approximation of the minimum number of lines of code that were implicated when you wanted to send one byte from one machine to another. So
wait, 30 million lines of code to send one byte a machine. Does it matter that it's over it? I'm assuming it has to be over like the internet. Is it?
No, could just be two machines next to each other probably. But internet was what I was doing. So I included the router's firmware in that calculation, but it wouldn't change that much if you didn't. Okay. And my point about that was that, look, when you boot, even just booting up a computer, let's just say it doesn't even do anything. I just turn it on. UEFI BIOS nowadays is like 2 million lines of code. So you turn a computer on and 2 million lines of code had to be secure. If it wasn't, you can get owned, right?
Yeah.
The instant you start loading an operating system, I mean, heaven help you, you load Linux or Windows, because then there's tens of millions of lines of code that are now running, potentially, right? And you don't even know which ones they are because it depends on which devices are loaded. It depends on what sort of things you're doing with the computer, depends on what versions of APIs people are asking for, right?
Is the implication that Mac loads fewer lines? Sorry, I just wanted to make sure I understood that.
Oh, no, Mac would be, I mean, Mac could even be worse for all I know. I just didn't do the math for that one because...
Oh, okay, fair enough.
No. There's no benefit to using a Mac. It's going to be in the same ballpark, yeah.
Okay.
And this is all before, I mean, then you tack on the web browser, have a few more 10 millions or tens of millions, depending on where they are at now, I'm not sure. Like I said, it keeps ballooning over time. So a lot of these were in the single digit millions at the time, and they added up to 30 million. Nowadays, they might add up to a lot more, like I said.
Yeah.
And the point of the lecture was to just try to underscore to people two main points. One, that it's unclear if this is at all sustainable if you are trying to achieve certain goals. Those goals are not necessarily performance. Obviously, performance does suffer as a result of this, but it's less of a concern for performance because a bunch of stale code that's sitting around that just doesn't get used very often isn't really that big of a deal for performance. Right. So my thing was more about security and innovation. So security is implicated here because anything that could be reachable in these lines of code that an attacker can provoke is part of the attack surface. So even just knowing which of those 30 million, now probably 100 million lines of code you should be worried about is itself almost impossible because you would have to do a security audit of all 100 million lines to figure out which 100 million lines you should actually pay attention to, right? Right. So that's a huge problem right there. For example, if I were to ask you right now, hey, which of the 2 million lines in a UEFI BIOS need to be secure? Your answer is probably, I have no idea because I don't know what's in the UEFI BIOS, which would be basically everyone's answer except the people who made the UEFI BIOS. So if we were to conduct an audit, we would be loading up 2 million lines of code that we've never seen before and trying to probably run some kind of static analysis tools to help us narrow it down. But really, could we? Because it's BIOS and we don't really know exactly how those things might get mapped in and dispatched to because they're not all going to show up as literal API calls. They might be things that are like interrupt table driven or who knows what. And you can't just use hot analysis like what actually got run because it could depend on which machine or what the scenario is. So my point in this lecture is like, look, if you care about security, our current development practices probably are just straight up unsustainable. Even at 30 million lines, which was already at in 2015, you're done. The thing we have where every month there's a new giant list of CVEs of all these exploits that people found, that will go on forever. It will never stop. And you don't even have to add new code. You could freeze all the code we have today and never write a single new line of code, and those CVEs will never stop. They will just keep going. And the reason for that is there's already enough code just sitting around that we just simply don't know what it does or how it does it in any real security sense that people will keep on finding these things, right? So that's one point. The other point was, and this is the one I care more about, because like security is one thing. Some people really care about it. And if you do, I think you should really care about this level of bloat because it's a huge issue for security. Yeah. Way more than it is for performance. Way, way more than it is for performance. Because performance, you can focus on code that you know runs a lot. Security, you can't. You can't just keep yourself isolated to code you know that runs a lot. Right?
It's if it runs at all.
Not if it runs at all, if someone could get it to run at all. And there's a difference between those two things. Okay. Right? Yeah. You have to figure out whether there's anything an attacker could possibly do including all of the code, all of these 30 million lines they do have access to, because some fraction of that is running in user space. Given all of that, can you prove that the rest of these lines are somehow secure? And the answer is, of course, you can't. No one has any idea how you would ever do that, and we probably can't. So that's one thing. But the other thing which I care more about, but which is also which is a separate problem, is innovation. If your fundamental infrastructure requires 30 or 40 million lines of code to work, some of that is pure bloat. So it's possible that some of that is just stupid. And that's fine, because we could mount an effort to start reducing this amount of code, or from an innovation standpoint, simply not care. For example, if something in the Linux kernel is a thing that was for driving the smell production USB device that allows gamers to smell certain smells that their game triggers, and we just frickin' delete it to make the Linux kernel's attack surface smaller, that's fine. We could do that, right?
Yeah.
So there's some of that. But for the most part, if we want to talk about what the cost is to innovation, if we want operating system innovation, platform innovation, BIOS innovation, the minimum amount of necessary code to be compliant, or I shouldn't say compliant, compatible with the current typical hardware, webcams, graphics cards, USB keyboards and mice, pen, tablet surfaces, speakers. There's a list of these things. If that fundamentally requires several million lines of code, because we have just done a bad job standardizing and unifying the way we talk to hardware and making sure that it is simple and that the hardware doesn't introduce additional complexity, so that we're actually keeping the hardware interfaces simple and their behavior more simplistic, we're basically foreclosing the possibility of anyone ever making another operating system, right? We may well have gotten ourselves in a position where no one will ever make another operating system. They will simply fork Linux or do some mod of macOS or butt pirate the code to Windows off of one of those leaks and use it, right? But what they're not going to do is actually be able to innovate in that space, which I think we do actually need. And so the other point I was trying to make with that lecture was that if we rethought how we deal with hardware and brought it back to a simpler method of just more straightforward memory mapped I/O, where the drivers were more in user land than they are in kernel land, we could foster more of this kind of operating system innovation. And that's not only relevant to people like me who want to see operating system innovation. I think it is also relevant to go all the way back to the original thing I said about Docker containers. If what you care about is being able to deploy code easily in hypervisors or things like that, the more we simplify that down, the more streamlined, cost-effective, efficient, and reliable that process will become, because there won't have to be so much jank. Oh, I had to also ship the entire Linux kernel on top of the hypervisor, because otherwise I can't figure out how to talk to this network card or things like that, would no longer be a thing. It would be trivial for you to write to high-performance network cards just in general, and you wouldn't have to go out and do anything special to make that happen, right? Et cetera, et cetera. So hopefully that gives you a perspective on what I was talking about in the video.
Yeah, I can see how this is a problem, I guess is what I'd say after listening to all that. What do we do? Because it doesn't sound to me, I mean, it's exactly like you said. This is not a performance problem. This is like a maintainability problem. It's a barrier to creating new software, that we have all of this code that it would be wrong to say we have to understand it, because clearly we don't. But we should. No, we don't. If we wanted to move forward, we should.
Well, and the security concerns are the other one, where it's like, well, yeah, we don't understand it and don't quote unquote have to, but then also the cost of that is every week there's a set of patches.
Right.
And a bunch of things that aren't patched that right now someone is using to exploit machines because they're, a state actor or a very sophisticated hacking group who isn't going to release those exploits that they found. And that's a real thing that happens in the world, right? So we pay a cost for our lack of understanding of these systems, and that is intrusion by sophisticated groups. Random idiots on the internet will not, because they are using, known exploits that are just out there, and that's not as much of a concern. But if you really wanted something to be secure from sophisticated, technical people, NSA, those people who know what they're doing, right? And actually put resources on this sort of thing. Yeah, there's no way. There's no way. They are going to be ahead of you because they're spending all their time doing it, and they'll find some things you haven't found yet just by random chance. They happen to look somewhere before you looked there. And vice versa. You'll find some things they haven't found, but that doesn't help you, right?
Right.
You need to have found the things they will find before they find.
This is feeling pretty gloomy.
Yeah, it's a depressing talk. Yeah.
Yeah. Do you have any recommended first steps? What should we be doing to at the most mitigate these kinds of problems?
So you'll notice that the talk is called the 30 million line problem, not the 30 million line solution.
Fair enough.
Right. So asking me to solve it is outside the scope of the talk. But what I point out in the talk is I was like, this is the kind of thing where we could be making some progress. If you take a look at initiatives like things like Raspberry Pi or things like that, where they're making small, known platform computers, right? Currently, 100% of those, not 95 or 50 or 20, but 100% of those kinds of projects are not trying to push the hardware in a simplicity direction. Raspberry Pi is a classic example that is built off a Broadcom chip where the GPU is what boots the system and starts the CPU running. Not a lot.
I had no idea.
Right?
That's hilarious.
Yeah, it's basically it's an integrated chip. It's got the graphics processing and the central processing on the same die, and the GPU is the daddy. It's the thing that's actually in charge, right? And the little baby CPU only gets started when the GPU says okay. So, in that sense, these projects, while I don't have any problem with them, I think it's cool to make small, cheap computers. That's a good thing to do. They're not really attacking this problem. The Raspberry Pi is just as complicated as an x64 machine. It's got all the same ridiculous nonsense hardware stuff going on. You have to read 300 pages of documentation to have any idea how the heck to even get the timers started on the thing, et cetera, et cetera. And that just doesn't really help us get anywhere. But if you imagined an initiative, if someone out there is listening who has billions of dollars and just wants to push this forward, you could choose to design a new SoC. Make a small computer project with an SoC where we designed it specifically so that it was as simple as possible to interface with its HDMI, its USB, and its storage, but that could just be over PCI, a PCI, or it could be a USB protocol as well, right? And it's Ethernet.
Yeah.
And if we did that, we could have an actual platform where we tried to get it down to the smallest number of lines of code to boot this frickin' thing, right? And that would get us somewhere. We could do that project, right? Now, unfortunately, I don't have billions of dollars, so I can't really do anything about it. But if one were so inclined, it's a money problem. This is not a technology problem. We can do this design. Because you're fundamentally
rewriting stuff, right? Like, rather than kludging on things that... I mean, that's why everyone does it that way, right? Is you're kludging on things that you know work, they're bits and pieces, but then you end up with 30 million lines.
Right. And also, similarly, like I said, because the hardware is so complicated now, one of the things that drives hardware is performance per watt or performance per dollar or both. So when people are trying to design a thing, they're not fundamentally looking at, will this be straightforward and secure to program? Will it be trivial to get this into a correct state and avoid having to have hundreds of thousands of lines of code to actually make it work? They're not thinking about that. They're thinking about, what is the cheapest USB controller I can stick onto this board that meets the particular criteria? Or what is the fastest USB controller I can stick on this thing so I can advertise my USB rates? At no time did anyone care how much work it was for the programmers. Right. So what we have to do is somehow get some altruistic money behind the idea that we should start doing experimental SoC design and chip design toward the end of simplicity, where we can see how much performance can we get with something that's still completely straightforward and trivial to program without millions and millions of lines of code sitting on top of it, micromanaging it, like a UEFI BIOS, like the set of Linux drivers you need to actually do anything on a Linux machine, and so on, right?
Right.
And so that's really what the next steps would be, but I have no idea how to actually make them happen.
Yeah. Well, the many billionaires that are listening to this show will definitely be reaching out soon. If they do, I'll be sure to forward any requests to you.
Thank you very much. I appreciate that. All of you billionaires out there, I appreciate that.
I have abused your knowledge for very long. I really appreciate you coming on. I think a lot of listeners are going to love this episode. Again, I'm going to plug Computer Enhance. Go check it out. Is there any of your other projects that you want to plug as well before we wrap up?
That's pretty much it right now. Thank you for the kind words. And yeah, Computer Enhance is really it. Believe it or not, it's funny that I'm on a Backend dev podcast because we are currently in the process of moving the site off of Substack for reasons that are largely amusingly related to like inflexible billing. Like they just don't provide us I just put it up on Substack because that was a place where you could sell video, like subscription-based video content. Yep. So if you would like to check out Computer Enhance, you can go there now. It's just computerenhance.com. And you can also follow the next few months, which might be fun because I will be posting things on there about my experiences moving things onto our own backend, which, will probably be very interesting to your listeners who have had to do all these same sorts of things that I am probably doing right now.
That sounds fun. All right. I will let you go after you answer one last question. Of all the Twin Peaks content, which part was the best? Pick a season, pick an episode. Whatever,
so like a scene, like what is my favorite scene?
Yeah. So like I'll answer it first to give you kind of an idea of what I'm looking for.
Yeah.
To me, the movie Fire Walk with Me was my favorite part of the whole thing. I feel like it really answered a lot of the questions that should have been answered in season 2 that we just didn't get. Okay.
So I'm probably on the opposite end of the spectrum from you, I guess is what I'd say. This shows how wide a range of Twin Peaks enjoyment you can have as a viewer. Yeah. There's like something in it for everyone, you might say. I really like David Lynch things, and I feel like he's at his best when things are not quite explained. So I think Fire Walk with Me is a good movie, so you get no disagreement from me there. But is it my favorite thing? No, because it is more about explanation and less about intangible things in that way.
Did you like season 3?
Here or there. I mean, again, there was too much explanation of what was happening, I think, in previous things that I so it's hard. Like, I wouldn't have a particularly favorite, like, overall thing, like season this or this particular movie, just because it's more about like I like it, the intangible things, right? So for example, I love the thing that's in my Twitter bio where the arm is like saying that there's Garmonbozia there in the dish, and that the Formica table's color is green, because it has like information content in it. Like it's not completely devoid of reason, but it is so far out there in terms of like what its real connection to things are that I just enjoy that kind of mystery a little bit. And I almost don't want it explained any more than that. So hopefully that makes some sense, because I feel like there's two sort of things there that you might want out of Twin Peaks, and I'm kind of on the other end of the spectrum.
It does. The thing is, it's like a guilty pleasure in the sense that I like it for the same reasons. There's so much mystery and so much to look into, but I'm an addict to understanding. And season 3 was great to me because it did answer some stuff, but then it felt like it proliferated the mystery. Like it also introduced a lot of stuff that then went on to be unexplained. So
yes, certainly. Yeah. And I do like those aspects of season 3 for sure.
Yeah. Cool. Computer Enhance, Twin Peaks. Go check them out.
Yes, definitely. Thanks for having me on the program. It's been a pleasure.